Okay, welcome everyone to the second talk for today. I'm very happy to have Annelot Bosman here, who is a fourth year PhD student at Leiden University, and currently she's visiting researcher at Oxford University. And her work is mainly focused on neural network verification, especially quantification of robustness of neural networks, which fits very nicely into the seminar series. And let's give the floor to you, Alnos.
Thank you, Jannis, and thank you for the invitation for me to present my work here. Today, I will be presenting some work that was accepted at the Leiden conference earlier this year. And it is indeed about neural network verification. And it's together with some of my former students, Aaron and Niels. In recent years, it seems like neural networks have exploded and are suddenly everywhere. But besides being very popular, they have a big flaw. And that's even though they're very good at classifying things like stop signs, you know, it is a stop sign, we classify it as a stop sign. Very small perturbations, such as those here, exaggerated a little bit, can confuse the neural network and have it predict wrong classifications, such as a do not enter sign here. And this is not so bad, but if you add a little bit of different noise, it suddenly will predict your stop sign as a 120 km/h sign. And that can, of course, lead to very, very dangerous situations. And if this seems like a far off example to you, the ones among us that have a newer car with, traffic sign recognition know how often the car misclassifies the stop signs or different type of speed limit signs. So, in order to combat this problem, there exists a field of neural network verification, and the goal of this field is to prove that a neural network behaves correctly under all allowed inputs. So, um, this mainly is supposed to give formal guarantees about the behavior, and we're using mixed interlinear programming formulations or set formulations for this, and this is exactly the overlap with this seminar. And typical properties to verify are things like local robustness, which assesses whether a network prediction remains stable under very small perturbations. And another property is safety, which is like if you have a drone and there's another drone, would the network ever make a decision that would have those two drones collide? So always see whether there exists safe bounds for the decisions neural networks make. And in this, so even though we can use mixed interlinear programming formulations or set formulations, we cannot directly use these traditional formal methods because they do not scale, and I'll come back to that. In this talk, I'll assume we're talking about local robustness if we're talking about robustness. So to repeat, that is trying to verify whether uh, a input remains correctly predicted under very small perturbations. Formally, you could say that within a certain bounds, and in the research, usually an L-infinity norm is used to define the distance between two images. Um, and a second parameter is the epsilon, where we say, okay, this is the maximum allowed perturbation. Check if for these conditions, the network prediction always remains stable. And some problems with, some ongoing problems with verifying local robustness is that neural networks are nonlinear because they have activation functions. One of the activation functions that's often used are value activations, which are piecewise linear, where the outcome of the activation function is zero if the input was negative, and it's the same as the input if the input was positive. Well, in order to encode this in a network, we need to relax these activation functions and linearize them. If you propagate these linearizations, there's these relaxations, through your network, you get an exploding feasible region. Because if you do a relaxation layer one, that has effect on the coming layers of the neural network. There's also very many parameters in neural networks, and that immediately means that there are very many variables in your MIP. If you're interested in how these MIPs are encoded, let me know later. I can explain that. Um, some other minor issues that we are running into in the field, but maybe not so relevant for today, are that there's no standardization for neural network formatting. So there's very many different ways to define a network. And if you want to go from those custom definitions to a mixed engineering program problem, that can lead to a lot of issues with just modeling from your neural network. And each verifier is a huge engineering effort because of the complexity of the problem. Then another issue that I've seen in the field is that we rely on the measure of robust accuracy to measure the robustness of our networks. And what this does is it gives a perturbation bound epsilon predefined and a predefined data set D, and checks what percentage of this inputs in this data set remain correctly classified given a maximum perturbation bound of epsilon. So this is just a percentage. And some of the issues with this is that this measure is very, very sensitive to your chosen epsilon. If you change the epsilon a little bit, your robust accuracy can drastically change. You also do not have an insight into which instances are problematic. So you, for each instance, you just get a, for each input, you just get yes, it's safe, or no, it's unsafe, but it doesn't say anything about if you change the epsilon a little bit. And it also doesn't say anything whether you're far away from being unsafe or far away from being safe. And it also has no guarantees of generalization to unseen inputs. So just adding some new samples might drastically change your robust accuracy. And we've tried to combat this issue by introducing critical epsilons. So on the screen, you see we assume a two parameter problem, so x1 and x2, so like two feature problem, and a decision boundary like on the yeah, here, okay, and two different classes, so the orange diamonds and the red rounds. Instead of saying, okay, we have a critical epsilon, which is a certain bound around your inputs. It's in L infinity, this is supposed to be a square, but I added around here. Instead of just saying, okay, we add the round to see whether it lies on the right side of the decision boundary, we're really specifically looking for the critical epsilon, which is the maximum perturbation radius that will not lead to misclassification. You could also, of course, choose the minimum perturbation radius that does lead to misclassification, but I'll come back later to why we chose it. This is a little bit of a more conservative choice. And then if you take, for a lot of instances, the critical epsilon, you can suddenly create a distribution instead of looking at a single number. And this has a bunch of advantages. So here on the x-axis, you see different neural networks for the MNIST data set. And then over the y-axis, you see the distributions over critical epsilons for a set of 100 images. It's good to know we only included correctly classified images per network. Otherwise, you would have a little bit more, weight in the tails there. And this perfectly illustrates my issue as before. So at a epsilon ball of 0.04, which is this red line, and 0.012, which is like an often used epsilon, net has a robust accuracy of 100% because none of the images are misclassified. Ooh. But then if you look at ReLU 4024, this one has a robust accuracy of 94% at this point. And only increasing the epsilon that you're looking at a little bit to 0.04, the robust accuracy of net drops to 49%, while the robust accuracy of ReLU 4024 remains at 86%. So even though at low levels, it might seem that net is way more robust. If you're looking at the critical epsilon distribution, you can clearly see that this could be seen as the most robust network of them all. So with that out of the way, we're looking at a different problem because these networks were feed-forward small data sets, and we could actually find the critical epsilon very close to the smallest adversarial example. So the smallest epsilon that would lead to an adversarial example. But in practice, it looks more like this. We have different epsilons between our critical epsilon that we could find and the minimum adversarial example that we could find, just because formulating this problem as a MIP problem is NP hard. It's not always possible to run it to completion. So we have memory errors here, we have timeout errors here, and the like. Yeah, so usually our solution is not as nice as having a single value. It usually looks something like this. And then if you look at our data, this was published in the Journal of Artificial Intelligence Research recently. But here on the x-axis, you see the epsilon values, and on the y-axis, you see the fraction for which the critical epsilon value is found. So basically, the more to the right a distribution lies, the safer it is. The more darkly printed lines are the critical epsilon values, and then to the right of that are the minimum adversarial examples found. So you can see that there sometimes is quite a large, oh, very sensitive mouse. There's quite a large difference between the critical epsilon value and the minimum adversarial example epsilon. By the way, these are all three the same architecture, just trained with adversarial training, and you can really see that it has a good effect on the robustness of the distributions. Well, so it's very expensive basically to get these distributions, and in this work that I'm presenting today, we try to make it a little bit less expensive. So we wanted to decrease the cost of creating these distributions because they're very insightful and they help us make informed decisions about what networks to employ in practice. But getting these distributions is incredibly expensive, like years and years of GPU compute went into the JR paper. So our proposal is to use just simple adversarial attacks instead of complete verification to find the minimum perturbations that lead to misclassification, and thereby actually giving a upper bound to our verification gap very cheaply. Because if you find an adversarial example, it proves that it's not safe for the size of the epsilon that adversarial attack needed. And how adversarial attacks work is that they get the network. So this is a white box attack. They do assume complete knowledge of the network. And then they try to maximize the loss in the direction of a misclassification. Yeah. And this is relatively very, very cheap compared to complete verification. Yeah. So to iterate, if an attack succeeds, we know that the input is not robust against that epsilon. But if we find no attack, we have no guarantees that it is safe. But it does provide us a fast and cheap upper bound. At least that's what we hope. So in this experiment, we use alpha beta crown, which is a formal verifier, and which is the winner of the neural network verification competition for the past 5 years now. And we used that as a baseline. Then we used some different adversarial attack methods as a way to evaluate the upper bound of the robustness distributions. So we used FGSM and PGD, which are the original adversarial attack methods, and then we used some assembly methods such as auto attack. We also use different architectures from previous works, and then we compare the lower bound of our distribution that we create with alpha beta crown with our upper bounds we get from attacks. And to our big surprise, we thought that alpha beta crown would always be better in finding an upper bound to our distribution. But in practice, we could see that, okay, so every time there's a data point below the red line, it means that AutoAttack actually found a better bound for our verification gap. So we thought alphabet count would always be better, but that's not necessarily the case. So that's a cool result that we found. Of course, you can use AutoAttack to start and find adversarial attacks within alphabet crown. But then alphabet crown also becomes an assembly method. And currently it does use some sort of finding of adversarial examples first, but apparently not as strong as AutoAttack. Um, yeah, some other results. So the runtime per instance, this is the average runtime per instance, drops incredibly if you're using a adversarial attack method. Of course, it's not fully fair to compare these numbers because alphabet crown does come with guarantees where the other ones don't. But you can see that the advantage in runtime is incredible. This also makes it possible to do larger data sets. Also, we see that the average upper bound we find between the different methods doesn't differ too much, while the runtime does differ quite dramatically. Also, we see that the relative marginal contribution, which is the proportional instances for which a method is the absolute best in finding upper bounds. We expect the alphabet crown to have RMC of 1, but it does not. There's quite some cases where it's equally as good as the others or even a little bit worse. So the conclusion is that we actually can use these very cheap methods to find relatively cheap upper bounds. And this one's not loading correctly, but for the first time, we could also use these attack methods to try and approximate the robustness distributions of the entire data set. So before that was absolutely impossible because it was way too expensive. Using just attack methods, we can provide a upper bound on the robustness distribution. And the light blue one that you can see is for 100 images, and then the dark blue one was for the full data set, and they don't differ too much. In order to do all these experiments, we provided an extendable code base called Verona, verification of neural architectures, and it includes support for complete verifiers, the attacks, and we're also working on lower bounding methods. You can find it in the QR code here, and it massively simplifies starting with neural network verification experiments. When I started, it was incredibly complicated to set them up because you needed like property files and different installation issues. So we try and take care of that with our software. And we're also trying um, to publish it in the machine learning open source software track. Okay, so to conclude, neural network verification is very expensive, but robustness distributions give us interesting insights in the behavior of networks that we do really want if we are going to use these networks in practice. In this work, we've shown that you can give some deep upper bounds that give you some idea of how your robustness behaves, but it does not come with guarantees. Currently, we're trying to do some experiments with state-of-the-art networks for ImageNet that come from Hugging Face. So those are like models with 10 times or 100 times as many variables as we could verify before, and see how that goes. And another question that we have is how can we get cheap lower bounds to the robustness distributions? Because those would give some guarantees where upper bounds only give you an ID and not a guarantee. So again, a QR code for the Verona code, and I have a QR code for my group's paper repository, where you can find this and many of our other recent papers. And then I want to thank you for listening, and I'll take questions.